Hello and welcome to our kind of bonus conversation related to Module 3. A couple things I want to talk about today. Go ahead and start off with probably the simpler one. Uh, Go ahead and clear my output and so on. So I thought I'd start off today talking a little bit about logging. Something that may not have came up in previous courses. See John just joined. Thank you, John. I appreciate that. Before we get started, any questions, anything you want to talk about, or go ahead and just jump in?
No, I think we're good.
Okay.
Looking forward to this.
Yep. So pretty straightforward, but it's something that I try to cover whenever I teach the introduction to data science languages, but not everybody does. It's kind of a generic software engineering principle that logging is a good thing, especially when you move past experimentation into things running in production in a real way. Jumping straight in, uh, uh, there's two different ways. We'll start off with probably Python's a good one. We're starting to clear all the output. Go back up here to the very beginning. So it's accomplished using the logging library. And generally speaking, it's already installed for you. You don't typically have to do anything. So the concepts that is important around logging is this concept of a log level, which is also kind of a degree of verbosity, so how much stuff is going to be spewed. The idea is there are times that you need to see a ton of detail, and there's times that you need to see some detail, and sometimes you only really want to know when bad things happen, right? So that's the basic idea. The way that you do that is by essentially at the time that you write the code that does the logging, you decide which one of these methods you're going to use, and you do so based upon kind of how frequently it's going to occur, what value it adds, how important it is. A good example might be if you're catching an exception, so you do a try and accept, and you catch that exception and you accept, probably a great idea to do some logging, and especially if it's something that should never really happen, that's potentially a warning, if not an error, depending upon what you can do from there, right? So the kind of the distinction that I would make with a warning versus an error: warning, something bad happened, but you were able to keep going. Error, something bad happened, you probably weren't able to keep going, maybe for that particular record or that particular file. Critical would be it's end of the world, right? You're giving up totally, going to totally shut it down. Working down from warning, info is oftentimes reserved for things like variables or phases of execution. It's not necessarily debugging information. It's not really any kind of connotation as something bad that it's occurred, but it may be just letting you know how far something is going through the process, right? But it's not noisy enough to be considered debug. So that's kind of the various levels. R does something very similar. We'll talk about it in a little bit, but it's a few less levels and slightly different names, but similar concept. So what this did was create a function for me called do some logging, because I'm going to do some logging, right? And the idea here is to show you what happens as we adjust the setting the log level. So initially it's set to not set up here. And what that basically is, basically the same thing as saying debug, right? We didn't really say what it should be, but if it's not set, then it does everything. We set it to debug, we run it again, and nothing really different, right? Because it's whenever you set it to debug, that means debug and everything that is more serious than debug or at a higher level than debug. And literally it's an enumeration under the covers. It's numbers 1 through something, 7 or whatever. So that's just a nice constant to make your code a little more readable. Now we'll go up to info, and you guessed it, debug drops off, right? Because we're only seeing info, warning, error, and critical. And it's not a bitmask sort of thing. It is literally one at a time of a turning the knob up or down. And again, it's so that you can strike that balance of, during early stages of your development, you probably want debug on because you want to see what's going on. Even if it's really, really noisy, that's okay because you need that insight. As you get more established, you probably don't need that much detail, right? So you'll probably want to turn it down until something bad happens and you need to diagnose what's going on. you can combine this concept of setting the log level so that it's coming out of a config file. That's something you'll see a lot in production type scripts, or potentially as a parameter that's passed into the script. Rarely do you go in and have to change the code to change the log level. Could occur depending upon how mature the code is. So the next step up, go to warning, and at that point, info drops off. Go to error, and you don't see warning, and so on. If set at the point you set it to critical, the only thing you're going to see are those things that are critical. You do have some additional options. There's a lot of stuff to this. I'm just barely touching the surface, but this one's kind of cool. Also, you can log to a file. Not really going to talk about that much, but you can you make a call to basic config. You tell it the file that you want to write to, where it's at, what level you want to go there, and it'll output to a file, including formats of timestamps and all kinds of good stuff, right? What this does is first we make sure that Colorama is installed, and that's just so that we can get some constants out of there. And this is setting up what's called essentially a handler, a streaming handler precisely. And what it does is you say to logging, take essentially the handler that you're getting and set a formatter on it so that we have this function that we're defining up here, which is a formatter. And what it does is do things like put the time in, put in a pipe, the color, and then the level name, and then resets the color, and then gives you the message, right? So it's literally what it's doing. And so now we can do some logging. It also, the very last thing here after we added the handler is we basically started with the handler that is the standard stream out, or standard out, and then we essentially are replacing it with our own, but we're kind of saving that, right? Do some logging and we'll see a whole lot prettier, right? You got a nice timestamp. You have some color coding that lets you really see what's important and what's not so important. So critical really stands out, right? And this isn't my code. I borrowed it, so to speak, from this GitHub account, and so definitely kind of worth color coding. If Googling color code Python logging would likely yield that result. And then you can also do some additional sort of things here. Here I'm doing a critical. This is just showing you that you can also do string replacement, right? So you do a %s inside of the first parameter, and the second parameter is going to be replaced into that. So you insert it here. Once you're done, you can also remove the handler, and then it reverts back to the previous functionality. So that's in, what is it, 10 minutes or less, Python logging. So pretty powerful stuff.
Cool.
Yeah, and it's really important, right? It's amazing that sometimes we get pretty far into the program and it hasn't came up, right? But definitely worth doing a little Googling on. Same sort of thing in R. And then I don't know who came first. They're almost identical. Probably R came first then, right? Because it's been around forever. Library logging. And you probably have to install that one, but maybe not. Depends on what all you have installed. Here I do something similar. I'm setting up a function that's going to do some logging. I make a call to basic config just to kind of make sure everything's in the right state. I do some log something, and you can kind of tell it defaults here to info and above, right? So we're getting these guys, not getting debug, fine, and finest. Probably that's what basic config is doing. Probably not a bad place for most things to start. That's where you're likely going to start. Similar concept. This one you pass in a string instead of a constant. And so we set it to finest, and you can see everything shows up, and it just natively does the color coding. So that probably tells you where the guy got the idea to do color-coded handling, right, for Python. Set the level to fine. Finest drops off. Debug. And it's like they don't exactly line up. Kind of these guys are pretty common, but it gives you this higher degree of fineness below debug, and you lose the critical, right? So that's the only real kind of differences between the two. I could see doing this one because there are times debug is, there's a lot of levels of debug sometimes, right? So If you've got something inside of a type loop that's really spewing, that's probably a finest, right? If you've got something in a not so tight a loop and you don't see near as much, that's probably fine. And then if it's high level information about what's going on, that's probably debug. And then if it's info you need to figure out what happened during a given execution, that makes sense as info, and so on. So a similar concept: as you set the levels, it turns down the volume, right? So that's pretty much R logging, very similar in nature. Good things, definitely worth spending some time. Make sense?
Yes, it does.
Yep.
Very cool.
Yep. Also, I learned, me poking around inside of a Jupyter, rather than installing the time execution thing, there's one that's built in that's awful nice. It was like execute time, right? And that's the one that we're seeing here with this nice little formatting. So
yeah, that's cool.
Cool stuff. So dimensionality, that was the other thing I was going to talk about. So this section we've talked about PCA, right? Principal component analysis. And that's kind of one way of doing it. So I thought I'd do a little bit about why we do it. And then basically other ways to do it as well. Along the way, reminds me, there is another extension. This is turning into a lecture about extensions, right? Called Codify, or Code Prettify. Sorry, not Codify. Code Prettify. So anyway, I'll show you in a minute. So the point of reducing dimensionality is this thing called the curse of dimensionality. And basically what it says is that as the number of dimensions increase, the amount of data that's necessary to be processed to sample it effectively increases exponentially. And we kind of intuitively know that, right? So as you add more factors, so if you go from 2 dimensions to 3, you need more data than you need with 2, right? So that's kind of the basic idea. You need a full range on each of those dimensions that come in. And so the way to address that is to reduce dimensionality. So to reduce the number of dimensions involved. And so the ones we'll go through here, and these are part of what I'm trying to show is the buckets they're coming out of, and then some of the ones in the buckets, right? And some of this you've seen in the past, but it may not have been explained as that's what you're doing, right? So feature selection, and we'll talk about that in a minute. That's one kind of common way of reducing the number of dimensions. Then feature projection or aggregation, and that's where things like PCA come to play. And then we'll talk about LDA, kernel PCA, a non-negative matrix factorization. There's a mouthful, so we probably just go with NMF. Autoencoders, which is coming from the realm of neural networks, and it has some advantages, but some downsides as well. And then a t-distributed stochastic neighbor embedding approach, so the TSNE, and then the UMAP, the uniform manifold approximation and projection. So these are kind of cool. I'm not gonna go into all the math. It makes your head hurt, right? But you can know what they do and know how to use them and when to use them, without necessarily being able to do all the derivations inside of it, right? So that's kind of the point. And then dimension reduction, k-nearest neighbor is probably one of the first things you learned, right? And certainly classification. So feature selection. And this basically, there's several ways to do it. One way is to get rid of those features which have low variance, right? Make sure I've run things that I need to run. Yep, I have. So just using feature selection out of the feature selection namespace variance threshold, right? So this basically goes through and figures out that, which is one of the dimensions, the first column was removed because it's very little variance, right? So kind of gives you some indication of things to look for. Univariate feature selection, similar sort of concept, and this is about figuring out the mechanisms of which one of those you want to get rid of, right? So another example, taking iris, because can't have a conversation without talking about flowers. and basically figure out, this got rid of basically two of the dimensions, figuring out that they don't necessarily add that much value, right? So if we care about what they are, we can display them. That's what it was before and after. And again, it just got rid of two of the columns. And while I'll pause here and talk about the other cool thing I found. These are things that are in most programming languages, right? But I'll make this maybe not so pretty. And then I got this handy dandy tool, right? I click that and it makes it pretty. Isn't that kind of cool? Auto formats for you. Doesn't like it if you've got a syntax error and you try to do it, but whenever everything works, it basically does some spacing and prettification of things. So it doesn't really change much, but does make it a little easier, a little prettier. That's that code _ prettify. So that's pretty much kind of the two feature selection approaches that I'll talk about. There are more. There are books on dimension reduction. Quite a few of them. In fact, I may even cite some of them in through here because it's there's a lot of stuff to it, right? And we don't necessarily approach it from that perspective. This is more hands-on, which is appropriate, I think. But at the same time, it's understanding the point here of why we do this, right? And it ends up being, as the number of dimensions increase to some point, it becomes intractable. We can't do it. Even with big data computations and distributed computing, it ends up being that you can't necessarily do it. Plus, some of the things just aren't all that valuable. So here's PCA. You did a great job on that one, by the way. And we'll go ahead and make sure it's pretty. It is pretty. Similar sort of concept. And made it print out so because it has a tendency to not. And these are examples I'm pretty much borrowing from the scikit-learn, right? So not necessarily anything new on my part, just basically showing the various examples. And you also have some choices here around solver, right? Which one of the solvers you're using. And you can see there's subtly different, but not necessarily hugely different outcomes. And there are more examples if you're so inclined. The PCA example with Iris, and this one was kind of cool. You may be familiar with this, but well, there's several things like this, but this is Binder, and what it'll let you do, it's kind of a free sort of environment. It's being sponsored, it looks like, by Google Cloud and a few other people. It takes a little bit, but once it comes up, you can basically, it's Jupyter Lab hosted, right? Similar like Google Colab or the various other environments, but you can take those examples, right? So an example out of scikit-learn and run them, right? So kind of cool.
That sounds like it would be handy. Now, what is Jupyter Lab compared to Jupyter? I've never really played with it.
It's the next version of Jupyter Notebooks. Not a ton of difference, really. I think it's their next version, right? And it's also probably an attempt at more of a premium sort of thing.
Got it.
You can install it. It's part of Conda, right? So the Anaconda Navigator lets you install it. I played with it. It didn't seem that compelling to me, so I just stuck with Jupyter Notebooks. I didn't see anything that I couldn't live without, and Jupyter Notebooks are just easier, right?
Right.
It's probably things like this GitHub binding and so on. That kind of stuff is probably a little more first class.
Binder, gotcha. Okay.
Yeah. And so here you can see it did the nice little three-dimensional PCA rendering of it from that example. But anyway,
Nice.
there's other things like that I've ran across. Binder, I think, is the only thing I've seen so far with Jupyter Notebooks. There's things like that for JavaScript. I've ran across them as well. So cool stuff. And it's really handy for an example, right? Because you can actually go in here and run it, and you could actually play with it if you're so inclined. You're not gonna save it, right? But you could fiddle with it if you wanted to move stuff around, right? I should be able to do this.
Yeah, really learn how something works.
Yeah, break it so you can understand it, then fix it. Hopefully
Yep.
hopefully that last bit, right?
Right.
Oh, it's probably because it's already on there. Anyway, I'm sorry. Was you saying something?
Oh no, sorry,
Oh,
my
no.
dog might have sniffed there.
Oh, okay. So another sort of a way of reducing dimensionality is the linear discriminant analysis, fancy word, right? LDA. Um, and it's some of these things are relatively complex, but um, you can fiddle with them and figure out which one works the best to do a comparison, and sometimes do visual inspection to determine what works the best, right? So pretty easy to do. Underneath again that same sort of namespace discriminant analysis, you pull it in and create an instance, run it, and take a look at and see what the predictions were, right? So and that was, did it print? Oh yeah, it did one. So that's the thing it said. So this one was interesting, I thought, as well, as comparing LDA to PCA in a two-dimensional sort of way, right? So we know what PCA is. We talked about it. LDA is doing something similar. You're looking for the attributes that account for the most variance between classes. So similar sort of concepts, different focus, right? LDA is supervised. That's one kind of distinction. You need to know classes. So it makes sense to do iris, right? Because we know their classes. And so here you can see PCA of iris, and here you can see LDA of iris. And you can see that's probably a little better especially if you're just doing a straight line, if you're not dealing with some sort of rotation, right? So different sort of projection. A few that would give you some grief. That guy's a problem, right? There's a few, but otherwise, pretty good job. And these are two that are pretty hard to tease apart most of the time as well. So definitely some interesting tools to play with, right? Not sure why that didn't work, but anyway. And then so there's also variations of PCA, including a kernel version of it, and it uses kernels to do the reduction. There's a lot of stuff into that. If you want to dig into it, we can. But short version of it is decomposition kernel PCA. This is doing it on the digits, right, data set that I'm sure you've seen. And it is, again, a way of reducing the dimensions. That one I've kind of struggled with a little bit because it kind of seems like the number of components should be 10, right? But maybe I'm thinking wrong. But anyway, maybe that's the components you can get to still classifying into 10 different classes with fewer than 10 components. Anyway, something to think about. I think it was this one, the NMF, complicated math, right? Don't worry about that too much. But this was about it basically is producing a couple matrices off of that, which are, one of them is like the vectors or the factors, and the other is like or components, the components and the weights essentially. And the basic idea here was, I believe, it allowed you to kind of preserve distances between things while transforming them to fewer dimensions. I think that was this one. Let's go ahead and run it and see here. So this is creating the W and the H, which is essentially the W is the weight. H is, I think, in this case it's talking about document. That's the other thing, is some of these things seem to be so tightly coupled to certain problems. Like topic modeling is NMF is, it's hard to find something that talks about it without talking about NMF, right? And it's hard to find something with using NMF that's not topic modeling.
Okay.
So they seem, there's probably cases where it's not, but yeah, definitely they don't seem to be common. The key concept, though, is that you're producing matrices that it seems to be important that they're non-negative. So not necessarily, it could be zero, but certainly not negative. This is kind of two different ways of representing the same thing. Um, yeah, and this is where you can see the final reconstruction is purely additive and has been shown that it's particularly efficient for images or text. So that's where um, it definitely seems to be very much in that domain. And that's probably part of the reason why these don't come up is we're kind of focused on more analytics, not so much computer vision or NLP, right? So, and I think this is where it told me it didn't really converge all that well. It hit the number of iterations, but it may not have converged. But still, pretty interesting stuff. And tools that, again, the whole point of this is whenever you're facing a problem and you think, gee, what do I do there's too many dimensions, what can I use? These are some tricks that are in your bag that you can say, there was something, what did he say that, oh yeah, maybe it was autoencoder. So take a look and see if that's something that, do some Googling and see if it works out. Autoencoders are, I've seen them before and actually used them before, but it was in definitely an AI sort of perspective, not in a data science perspective. Not that those two are mutually exclusive by any means, but I was doing some AI that was not necessarily at the same scale that you might do. So the basic idea of a autoencoder is you train it on representative data. But the problem is because you're training it on data to basically figure out a way of reducing the dimensionality based upon that data, like all things that are trained, if it sees something it hasn't seen something like before, it may not do very well, right? So that's kind of part of the problem with it is it does really well on the things it does well with, but not so well with things that are different. You've dealt with encoding and decoding before. Certainly you've used it without maybe even knowing you're using it, right? When you play a song that's or an MPEG or an MP3, that's being decoded, but it's a special type of algorithm, right? That's a depending upon which one you're using, potentially a lossless algorithm, not necessarily MPEG, but there are some that are. And that's another problem, so to speak, of autoencoders is they are lossy in nature. So if you take something, run it through it, and decode it, you've lost some fidelity, and that's where they do tend to produce lossy output. So that's not necessarily you could view it as a form of error, right? And all of these approaches that are reducing dimensionality introduce a certain amount of error. You can't reduce the number of dimensions and maintain all the fidelity because there's a reason all those dimensions exist, unless the dimension's not contributing, right? Then you can, right? But assuming it's a relevant dimension, then you can't really just throw it away and think you're not going to lose something because you kind of needed it or it wouldn't have been there, right? So this to me kind of seemed a little upside down, but I'll walk through it. You get input. It goes through an encoder, which is a connection of multiple layers of neural networks, and you end up with some sort of representation of that thing, so a code that goes with it. Then you can run it through a decoder and get back something that's somewhat similar to what was encoded. But again, not 100%, hence the lossiness, right? And so the reason that they're pretty compelling is it does do a pretty good job. So hopefully this will work. I've been having some trouble with my that's looking great. Let's see what happens. All right. Yeah. Running inside of my Windows subsystem for Linux, there were some issues with my GPUs. I'm not sure what's exactly going on. So basically here we're going through, we loaded up the NIMNIST or whatever it is, fashion data, right, which I'm sure you've seen before. It's basically the pictures of clothes and a classification of the clothes, so we can take a look at one of them. So there's a t-shirt, right, or something with some sort of logo or something on it. And so here we can basically decide how big we want to make the representation. So here we're going to do 32 by 32, so 1024 floats. And then we're going to do essentially some reduction of it, and then basically regularize it and so on. We're doing all this stuff so we can actually, and that's where it blows up. Yeah, it was working for me earlier. All right, well, I guess we'll skip over that. The end result, you do some training, and then some reshaping. Let's see, where was training? So we compile the autoencoder. Here you do your training, and then you do some prediction based upon it, and it works pretty well at the end of it all, is the gist. And I can't really show it right now because my subsystem is not well, and something to do. I'm running Windows 11, right? So they've, I think they've updated some of my drivers and such that broke my GPU pass-through, so I have to figure out how to fix that. I think we're near the end. This is the T-SNE or TSNE approach. This converts your basically things to probabilities, then does some I believe projection and so on. End of it all, we get down into something that's pretty easy to do. Again, this one is a little different. sklearn and Keras. Hopefully this will work. Yeah, it's giving me grief with my GPU. Anyway, so hopefully this will work. So we can load Iris again, basically create an instance of it and then do a fit transform. And then basically you can see reasonably good job separating them. Again, though, not as easy across the X dimension, but with some rotation you could get pretty close. So again, none of them are 100%, and Iris does seem to be one that's very challenging to get 100% right. This is I believe this is the last one, or next to the last one, because we got k-nearest neighbors at the very end. So UMAP, a uniform manifold approximation and projection. And this is, again, another dimension reduction approach. So you can basically use it as a replacement for the one we just did. So as an example, I've already got it installed, so we should be able to just go through here. This example is classifying penguins based upon the length of their bill, I believe it is. So here we go. Here's what the data looks like. And so, yeah, it's based upon bill depth versus bill length. I'm not real sure why we care, but maybe we do. I don't know. Anyway, the pair plot's pretty interesting. Shows you the species by the combination of various of the attributes and features. So that's pretty cool. And then we can do this basically some scaling. So we do a standard scaler, which is pretty common. If you're not scaling data, you may want to wonder why, because it seems like it needs to happen most times. Fit transform. And we do get back an array with 34 samples and 2 feature columns instead of the 4 we started with. So we reduced from 4 to 2, and then we can do our projection. And you can see pretty good, given that we've reduced the side, although you got a little bit of weirdness here and a little bit of weirdness there, but otherwise that's really pretty good. So this one I was pretty impressed with. I'm actually trying to try this on a high dimensionality challenge that I've been dealing with in a different sort of side project that I've been doing. But anyway, it's looking pretty promising there. So the last one is around dimension reduction with k-nearest neighbors. K-nearest neighbors, I'm sure you've done before. Nothing terribly exciting, but it is interesting to think of it in terms of reducing the number of dimensions. So we're let's see, this is Iris again, and it's about trying it with different levels of, or no, I guess we're doing K, but with, what is that, different algorithms. So K-nearest neighbors combined with things like PCA, LDA, and that one's actually pretty good there, and K-nearest neighbors. So that's pretty much what I have to talk about today. Not sure how much it helped, but hopefully it helped some. Any questions, observations?
That's interesting stuff. The comment you made about scaling data, that's something that I don't always do. Like, is it better to classify scaling as this is when you want to do it or when you don't want to do it?
I know that there are certain algorithms that are very sensitive to data of different scale, right? I'm pretty sure it's regression, if memory serves, is pretty sensitive to it. A lot of neural network type stuff is, so autoencoders would probably be susceptible. But it kind of, a lot of that, it depends, and typically when you take a look at an algorithm, they're going to tell you it should probably be scaled or not. But it's definitely a good idea. Some things I don't think are as important, like decision trees. I don't think it's necessarily all that important. But whenever, I'm pretty sure when, I'd have to look to be certain, but I'm thinking regression is pretty important.
I'm imagining a data set of just a handful of, elements, and, if scaling effectively demeans, like calculates the mean and then subtracts it from each value, are you decreasing variance? Is that the?
Well, what you're trying to do is your transformation shouldn't have anything to do with variance. It should be getting it where the range is roughly the same, right? So from -1 to +1, or from 0 to 1, with the preserving the same distributions is kind of the idea.
Oh, so you're scaling them relative to each other, not just within each individual field?
Well, you're trying to get like feature 1 and feature 2 have basically the same magnitude, right?
Gotcha.
So that's, and some things, it's almost like a graph, right? Think about it from a bar graph sort of thing. If you have something that's running from 1 to 1,000 and you have something that's running from 0 to 1, you need to do something, convert it to percentages or something so that it'll look the same way, right? Same sort of
Now
concept.
I get it. Thank you. Okay.
Sure.
That's much more important than what I was imagining, because I hear people say it's so important, and I never understood why it was doing more than I realized under the covers, the standard scaler.
Yeah, you're basically kind of trying to get it from, it's a transformation, right? And you should, in theory, be able to, like a function, apply it and then reverse it and get back the same stuff, right? That's the basic idea. Yep. So it should anyway, yeah. So
so this is kind of a weird question, because I think it's really obvious what the answer is, but if you train a model with scaled data, then you need to feed it scaled data when you're scoring, correct?
Yeah, you would.
Yeah. Okay. Yeah.
It'd be a good idea. It's the same thing with, like in neural networks with models built in that. If you do some sort of processing to the data during the training phase, you want to make sure you're doing that during the recognition phase, right?
Right on.
Right. So if you're downscaling the images, then you want to downscale the images, right? That kind of thing.
I think I realized why something I was trying to get to work 7 years ago or so didn't work. I don't know why now.
Yeah.
Awesome.
Yeah.
Cool.
Glad it helped.
Yeah.
All right. So I guess with that, we can wrap this up. As always, if you have questions while you're watching this, let me know. And thanks for joining again. Always appreciate having somebody in the room. If you have any questions, shoot me an email. That's what I'm here for. I look forward to our work on the next module.
Sounds great. Have a great night.
You too. All right.
Thanks. Bye-bye.